image pyramid in your book section 3.4 and 3.5.3. And again, the slides are available online. You know where to get it, right? Some of you feel confused. In our e-learning platform announcement, okay, there's no something. Okay, who doesn't know it? Do you know it? Okay, let me show you. Okay. Okay, this is our e-learning platform. Get into the announcement. You can see this is the post about the slides used in this course. Okay. Right? So let's talk about the term project. So you know the total points of the term project is 35 points. And it is separated into several different parts. In your proposal, there will be 5 points, and your pitch 5 points, midterm report 5 points, and the final project presentation 10 points, final project report 10 points, totally 35% of the class grade. And in your pitch and final project presentation, every team will present your plan and your results. And I ask all of you, the reviewer, to give 15% of the grade, and the remaining 85% will graded by me. Okay, and all of your written reports will be graded by me only. In our previous course, there was an interesting question. Some people wanted to implement an algorithm published in a paper, but he has no idea how to find any existing implementation of the code. So there are several ways to get or find the code of a paper. First, is check whether there is a URL in the paper telling readers where to find their code. If there is, that is the most convenient way to get the official implementation of an algorithm. But sometimes the authors don't publish their code don't mention their code in their paper. So for us, we can check their website, in particular the first author, because usually the first author is the person who implements the algorithm. Otherwise, check the corresponding author. Usually that is the one, because usually the corresponding author is the advisor of the first author, if the first author is a student. Otherwise, Google it. Sometimes there is third-party implementation of the algorithm. Otherwise, check the website, paper with code. Yeah. Okay. This is the website collect all papers, in particular in computer vision, with code. And otherwise, check GitHub. If all of those methods do not work, the latest way is to send email directly to the authors. And sometimes it works. Okay, so let's go back to our term project. this slide has been shown in our first course, and I want to emphasize again, your term project must be either it is existing work and you need to check the reproducibility or check the generalizability on other data sets. So let's go back. This is a case if you cannot find a copy of the implementation for an algorithm. It's very interesting because that is your opportunity to implement it for your term project. Otherwise, you can imagine certain ways to use an existing algorithm for other type of method applications. So that's the case B. Or if you are interested in improving some existing algorithms, that is okay. That is the case C. So all of the three approaches is a way to do research. Okay. So in the term project, I encourage you to do certain level of research up to your interest. Okay. And in this course, I will show you many pieces of MATLAB code. So here, I want to make a brief introduction to how to install MATLAB for you. As I mentioned in previous course, MATLAB is a very expensive software package. But when our school purchased the license already, so all of you are free to use the software. And how to do it? First, go to our school software download website. And there's a key, a license file, and an installation document. So this is the key. And this is the license file. And this is the ISO file. You download the ISO file. It's quite large, around 20 plus giga, depending on the version. Okay. And in the license file, it is a text file containing the description where to connect to the server. Okay. And then after downloading the ISO file mounted, you can find execute file setup latency in bin Win64 folder. Okay. Then install it. You will see a page telling you what product you need to select. For our cases, we only need an image processing toolbox, so that for some image-related functions, say F-special, it can create the filter kernel, or IM filter, it can apply a filter kernel on an image, or FFT2, the two-dimensional fast Fourier transform function. All of them are included in the image processing toolbox. And the MATLAB is the main program. You need to launch it to edit your code and to execute to see the results. And the network license manager, we need it because our license purchased by our school restrict the usage by, it only allows us to use MATLAB on campus. And it will verify your location by checking your IP address. So your device or your PC need to be connected to our campus network. Otherwise, you won't be able to launch MATLAB. So if you are not on the campus, you need to connect to our campus VPN at first. Okay, so let's look the path at first. So this, what is this? This is okay. This is title. Gala contemplating the Mediterranean Sea, which at 20 meters becomes the portrait of Abraham Lincoln, homage to Roscoe. Roscoe is another artist. Okay. So let's take a detail of this tent. So this is Gala. She is the wife of Salvador Dali. Okay, so take a look. This is Salvador Dali, and he was painting the plant. And Mediterranean Sea. Where is the Mediterranean Sea? Here. This is the sea, and this is the window. Okay, and so at the first look, it is a plant, window, woman, and sea. But if you go far away, 20 meters later, it will become portrait of Abraham Lincoln. This is I created these images to simulate the images you will see at a distance 20 meters far away. And what is this? So do you see the similarity between this image and this image? Okay. Then this is Abraham Lincoln. He was the 6th president of the United States. And I created this image. It looks like a low resolution image, but in fact it's not. I duplicated 1 pixel to 20 by 20 pixels, so it looks like a blocky. And this is my method code. So let me explain it. First of all, I load the image lincoln.jpg, and then I downsample it. I shrink it to 1/20, so it's become the small one. This, okay. Then I upsample it 20 times. But I use the nearest neighbor method, so it means just duplicate 1 pixel to 400 pixels. And then I create this image. So take a look of this. This is Dali's tent, and this is image I create. And if you look at this point here, you can see this is the portrait used by Dali, and in his image, in this photo, Dali is holding the portrait, and he tried to create something very interesting. And this is the brief. Okay, when Dali was young, this is Gala, Dali in the mid-ages, and when they are old. So what I talk about that tent. So this is a question. What does a low resolution image still make sense to us? What do we lose? So this is a low resolution image, and this is the source high resolution image. For us, the sense or the meaning of the two images are almost the same, but apparently their resolution are different. And what do we lose in the low resolution one? Any idea? Yes, please. Right? That's right. That's right. Okay. And other suggestions? Yes, please. Yes, good. That's a good answer. Any others? Well, that's fine. So combine the answers of the two classmates. You got the hint. The hint is, in the high resolution images, we have more data. In terms of what? In terms of details. So where are the details? See there, you can see the texture among the leaves, but in the low resolution ones, those details disappear. Okay, so we are going to show you an interesting image. So this is called hybrid image. Oh, this means if you have an elephant and if you have a leopard, then you use the low resolution data from the elephant and high resolution, low frequency data from the elephant and high frequency data from the leopard, and combine them together, you will get a new image. The image, when you look at it at a short distance, it looks like leopard. But when you stand far away to look at the image, it looks like elephant. So this is very similar when we look at the Dali span. When we are at a short distance, we look at we see Gala and see the Mediterranean Sea and see the window. But when we are far away, we lose the high frequency details, and we only see the low frequency signals of the image. So it will be an elephant. Another example is for the high frequency details comes from the cat, but the low frequency details comes from the guy. So when you look it in a short distance, or when the image is very large, you see the fur and the textures of the cat. But if you stand far away and see a very small image like this, then those high frequency details disappear, and you see the image of a guy. So how do we describe or measure frequency in image? Okay, so the ideas come from Fourier. Fourier was a French mathematician, and he had the idea any univariate function can be rewritten as a weight of sum of sine and cosine of different frequencies. So pay attention to the frequencies here. Okay? And in his life, most people, in particular those great mathematicians, doubt the idea, how to prove it. Okay? And those famous mathematicians include Lagrange. He is famous for the Lagrange multiplier, which is used to find the optimal solutions in when you try to solve a optimization problem. And Laplace is famous for its Laplace operator and the Laplace filter. This is the definition for Laplace operator. And Poisson is famous for the Poisson distribution. This is the equation for the Poisson distribution. So among the three mathematicians, Laplace research is most close to yours. So let's take a look of the discrete Laplacian operators. Okay, it is defined by this is a partial derivative for given an f function, a single two-dimensional function. Okay, so there are two variables, x and y. So this is definition for the partial derivative for the x direction. And this is the second derivative of the f So it is written in this term. Okay, so we can combine some terms and get this formation. And this is the second derivative for the y-axis. So also it's a case. We combine the second derivative for x and y. So this is a Laplacian operator. Okay, and if you combine of that, it will look like this. So this is the basic term for discrete Laplacian operator, and this is the extended term. Okay, and you have seen some filters in previous course. So this is the Sobel filter, and this is the Gaussian filter. Sobel filter can be used for what? To detect the directional edge. And the Gaussian filter can be used to blur an image. And the Laplacian operator or Laplacian filter, it can be used to find edges. So this, given this example, okay, this MATLAB code, okay. So, okay. So this is Sobel 1, 0, -1, 2, 0, 2, and 1, -1. And we use, I should say, I wrote this MATLAB code here to help you be familiar with MATLAB script. I should ask you a question at first. Whom of you have the experience of using MATLAB? If you have raised your hand, only you? Okay, fine. Okay, so that's the reason I want to write this piece of MATLAB code so that you can copy this script and test to your own MATLAB. Then you can run it. Let me do a demo. Okay, this is our MATLAB user interface, and I launch the filter. Okay, it looks like this. So, okay. The script, the first line is I will create a zero matrix with height 9 pixels and width high pixels. And then this is the filter, Sobel filter I will use. Then I put the Sobel filter into the center of the matrix. Digger command will create a new window. And the serve Sobel means use serve function to create the shape of the Sobel. Okay. So if we run our code from line 1 to line 7, okay, then I get, okay, it's another screen. So how to move it? Let me see. Okay, I got it. Okay, here. Okay, so this is the mesh function. It can create a surface of a matrix. And then let's go on to for line 7 to line 9. So sigma, it is the parameter for the Gaussian filter. Okay, it means the radius of the distribution. And I use F special. It is a function of MATLAB to create a certain predefined filters. So I assign it the Gaussian filter, and the size of the created filter is 9 by 9, and the radius is sigma. And I use figure again to create, and then I continue and generate the second image. So this is Gaussian. And the third, for something interesting is, in MATLAB, you can use the rotated 3D to change your viewing angle. So this is the interesting feature of MATLAB. And the last is the Laplacian filter. Again, we use F special function again, and assign this tape as Laplacian, and also alpha is the parameter of Laplacian. Then we run the remaining code, and we got the Laplacian filter here. Okay. So what I want to show is I show those code on our slide, and you can download the slides so that if you want, you can reproduce my results using your own MATLAB program. Okay, so the meaning of a Laplacian filter is it is a unit impulse minus a Gaussian filter. So this is the Laplacian filter. It has many parameters, but how large is the unit impulse? Can the unit impulse degrade to another Gaussian filter? It's okay. So the meaning of the Laplacian filter is a filter created by two Gaussian filter, one minus another. So what can we use the Laplacian filter? In this case, it can be used to find edges. Okay. So this is a input image, and then we apply Laplacian filter here, and it will generate the first a second derivative like this one, and we find where is the pixels. It will cross the 0 value. Okay. So for a dark part to a bright part, it's like this. From a dark part to a bright part. And then if we apply the first derivative filter, this will be the gradient. Okay. And then if apply it twice, and then there is a change from positive to negative, or from negative to positive. So we can search for any pixel. If it is a 0 crossing, then it will generate results like this one. Those pixels with crossing 0 are edges. So okay, so now we need to recall some high school math. So this is the definition of a sine function. Okay, the meaning of sine is given a unit circle, and the sine is the value of its height at this point. So this is sine. Another part is cosine. So remember, there is the equation: the square of sine plus the square of cosine equals to 1. Okay. Another definition of sine, given a triangle with a vertical angle, then sine equals to the opposite over hypotenuse. So it's very similar like this one. If we draw the sine function from negative 2 pi to positive 2 pi, so this is the shape of the sine function. All right, so we slightly extend the sine function. Sine function is well defined to a sinusoidal function. So if we set a as 1 and theta as 0, then the sinusoid function will be reduced to the sine function. So a means the amplitude. So given a as 0.5 or a as 1 or a as 2, you can see the magnitude of the three different figures change a lot. And f is the ordinary frequency, and omega is the 2 pi f. It's angular frequency. The difference of them is when we say frequency, we usually don't mention about the time, the magnitude of 2 pi. But for a sine function, if we use omega, it means a circle of the 365 degrees. So, and the phi is the phase. So let's take more examples. Okay, when we use the frequency as 0.3, so there will be less circles because the frequency is smaller. If we use f frequency as 1, the f frequency as 2, so the higher the frequency, the more the oscillation or the cycles. Okay? And the meaning of a phase is just a shift. So phi as 0, so it starts from 0. And phi as 1, so you will see all of the wave shift for 1 unit. And if phi as 2, the wave shift furthermore 1 unit. Okay. And also this is the MATLAB code. So this, because MATLAB only deal with values, so it cannot draw a curve. So how to draw a curve? So I create an array. The array starts from 0, 0, 0.1, 0.2 to 20. Okay. So let me run it to. Okay. Run it. Okay. Let's run the first step. Let's clear all variables, right? And run the first step. So this is my x. It starts from 0 and it gradually increase. Then I created a variable. You will see a here. And I create the f frequency variable. And I created the omega. So omega is equal to 2 times pi times f. And then create a phi. Then, so y is what? Y is the output of x. So given x, I use the sine function and its frequency times x plus phi, and I will get y. Okay, so I will get my y here. It's also an array with 201 elements. Then I plot xy. So this is the convenience of using MATLAB. Just a single script, we can create a figure. then we create a figure like this one. Right? And the remaining squares is I can set the axis of the figure. So if I now it's okay. The x-axis is from 0 to 20, but the y-axis is from -1 to +1. If I okay, so for let's go back to this. Okay. Because I want to let the three images easy to compare, so I control the range of the y-axis. Let all of them become -2 to +2. Okay. So in my code, I need to use the axis command to control the range of axis and the y-axis, so that the three images will be in the same scale. And okay, let's. Okay. If I call the step, okay, then see the y-axis, its range become -2 and +2. Okay. Then I will create a title here because the figure has no title. Right. That. Now you see the title here. And finally, if I use save as, then I can save the image into a PNG file. Okay. So it means get current figure GCF, and the name of the output file will be the A plus what F plus what F equals what and B plus, and the final the image type will PNG. Okay. Right. So okay, let's now we know we can control magnitude and frequency and phi to create numerous type of sinusoid function. And given this function, for example, it can be viewed as a combination of two sinusoid functions. And this one, its frequency is here, and its magnitude is here. And for this function, its frequency is 3 times of the left one, but its magnitude amplified is slightly smaller. So for this case, this is a square wave. So how to find those sinusoid function to reconstruct the square wave? So let me show you. It is first, we can combine the two functions and get this one. And we can add another function, relatively smaller, to get this one. And furthermore, to get this one. And furthermore, to get this one. And even another to get this one. And okay, if we want to get a square function, then we can apply a series of infinite sine functions, and this is a frequency sequence. So it's become a spectrum to get the square wave. So this idea is quite common, in particular for the voice or signal. Usually, you may see this. This is the voice wave. Okay? When you use some video auditing software, you may see this like. So this is the x-axis is the time. So there is a unit of seconds. And y-axis is the volume of a certain of the voice. Okay? So for a signal of voice, we usually will see, okay, some of the voice are high frequency. It means the peak, the C. And some of them are low frequency. It's a down, low sound. Okay? So if we convert the voice wave into different frequency representation, then we will get a figure like this one. For certain frequency in terms of hertz, then what is its volume in terms of decibels. All right, so this is for voice. But how about for image? So this is the case. This is an image. There is a mini tent, and there is a cat inside the tent. Okay? Then we can convert it to, I should say, we present the image using frequency. So this is the intensity domain. And this image is the frequency domain. So Fourier transfer is the tool to help us transfer an intensity domain image to its frequency representation. And how to interpret the result? It's like this. So first see the color bar. So the color of a pixel means the magnitude of the value in the frequency domain. And the location in the frequency image is when the pixel is close to its center. It means the low frequency signal. And when the pixel is close to the border, it means the high frequency signal. So from this image, we get this frequency image. It means in the original intensity image, there are many low frequency signals. So this you see here, the color is very close to red. The red means large values. And you also can see there are two. So this is line. The color is around yellow, and this is also around yellow. It means there are some strong vertical frequency. So what is the strong vertical frequency here? I think it is the floor, because this is the wooden floor. So you can see some certain type of frequency there. Okay. So it becomes the diagonal frequency. And what is the horizontal frequency here? Okay. As I see, maybe the pattern of the curve on the leg of the cat. There are some horizontal patterns there. Okay, so how to calculate? Okay, how to actually? Now we have the concept. Fourier transformation is the tool to convert an intensity domain image to its frequency domain. But how to calculate it? What is mathematical expression? I need to begin with Euler's formula. So Euler's formula is, this is the natural number E, okay? The J is the imaginary part, so this is the complex number, not a real number. So E to the cosine theta plus J is the imaginary part times sine theta in terms of this image. So you can imagine J is the axis of the imaginary value. So this is positive J and this is negative J. So this is positive real number and this is the negative real number. Okay. So take a look at this. Say J is the imaginary part, and if theta is half of pi, then E J half of pi, it will be this point. And when it times itself, it will become rotation to the half of pi degree. So it will become this point. And then if it multiply it again, it will go to this point. And then further again, it will go back to the next real number 1. So the Fourier transform, it is a real to complex function. Or furthermore, precisely it is a complex domain to complex domain function. But because our input of image, all of the values are real. So for our application of image transformation, it is a real to complex domain function. Also, this is a definition of Fourier transform. For a univariant function, hx, it will be the integral of the function with exponential to the order minus j omega of x in the dx. So, because according to the Euler formula, the exponential e will become the cosine omega x minus j times sine omega x. Then usually we will use the notation. The big F, it means a Fourier transform from small hx to the capital omega, h omega. All right, math. It's difficult for the first class. All right, so let's take a break. So you can see on our e-learning platform, there is an assignment, and it will due today. Okay, this is the team member list of your term project. So let me do a quick survey. If you find if you have built up a team already, raise your hand. All right. Okay. So because there is a lady who is looking for her team members. So for you, because the maximum members of a team is 5 people, right? So if your team is not fully occupied, only 4 or less people, could you raise your hand? 1, 2, 2, 3. 1, 2, 3, 4. Okay. So, do you belong to the same team? Do you belong to the same team? Would you mind to have one more helper? Because you have 3 team members, right? 4. Okay. So, would you like to talk with them? Because either of then has 3 or 4 members only. So do you know them? Are they your classmates? You can, okay. Maybe you can use the next break to have a discussion with them. All right, so this is the notation for the Fourier transform, the big F. And also, there is the inverse Fourier transform. So this is capital H omega. If it times e to the order, say, omega x, and integrates in terms of omega, and then it can go back to its original input function, hx. So this is a symmetric transform and inverse transform. So the notation of the inverse transform is big F and -1 and the big H function. Okay, so let's discuss the relationship between convolution and Fourier transform. So the Fourier transform of a convolution of two functions is the product of their Fourier transforms. So G and H are two functions. If they convolute together first and apply the Fourier transform, the result will be the same as the Fourier transform for the first function and the Fourier transform of the second function, and tie them together. And the inverse Fourier transform of the product of two Fourier transforms is the convolution of two inverse Fourier transforms. So if we have two functions, tie them together and apply the inverse Fourier transform, the result equals to inverse Fourier transform of the first function convolute with the inverse Fourier transform of the second function. Right? So the conclusion is convolution in the spatial domain is equivalent to the multiplication in the frequency domain. And okay, so let's recall what's the definition of a convolution. So this is the definition of a convolution. Given an f function and a g function, okay, their convolution is f and its variable times g is variable in terms of t minus tau and the integral together. Okay, because the tau and the t minus tau can be exchanged, so it can be t minus tau for the first function and the tau for the second function. And let's take a look. So say g is a unit function. It means between 0.5 and -2 +0.5, the value is 1. All other values are 0. Okay? And the g is also a unit function. Then the convolution of two unit functions will become the result. This will look like a triangle, but it's still a function. Okay? And then let's take another look. So now g is still a unit function, but f looks like a log function, partial log function, like this, the blue one. Okay. Then the convolution of the two functions will be the black curve, like this one. So this is a definition in mathematics of a convolution for one-dimensional function. Okay. So now we are going to prove the convolution theory. Okay. Because this is the definition for a convolution. G and H is tau and t minus tau. So So this t is the variable in its convolution. And this is the definition of the Fourier transform. Fourier transform, the big F, it means integral from negative infinity to positive infinity, the function times exponential to the order negative, say, times omega times t. Therefore, the Fourier transform of the convolution will become this formula equation. So the inside part is the convolution. Okay. The outer part is the Fourier transform. And so now we create a new variable t at u plus tau. Okay. Therefore, the dt is still the same as du, and the equation here, okay, it will become. So let's take a look here. So this is t from negative infinity, and now it becomes negative. U becomes negative infinity because tau is a given value or fixed value, so it doesn't change. And now it becomes du here. And for here, it is, so here is t. And it becomes u plus tau. And the u minus tau here, it becomes u. So it's just the variable change. Okay. Then from this equation, because the exponential term can be separated to the multiplication of two exponential terms. So we separated the exponential term here. It becomes the first part, e minus j omega tau here, and e minus j omega u here. The u plus tau becomes tau, and u separately. Then we can separate, because the hu term here, it is all the same within the integral. So we move the hu term out of the integral. Okay. So the inside term becomes this. So what is this? This is the definition of the Fourier transform. So we get the Fourier transform of G. And so this is a fixed value. So we can, if there is no u variable within the term, so we move the term out of the integral and get the remaining part of this one. So this is what the definition of Fourier transform. Okay, so we get this is real. So this is the convolution theory. So because of the convolution theory, there are some properties of the Fourier transform. First, this is linearity. If two functions with their coefficient, their Fourier transform will be the same as the coefficients move out, and then combine them together. Okay, and recall, Fourier transform is a complex domain to complex domain transformation. But first, all of our input data are images. Images have no imaginary numbers. All of them are real numbers. Okay, so for real signals or for images, the Fourier transform images are symmetric about the origin. And we will see many images figures later, and you will see the property. Again, remember, we transform an image to its frequency domain, and we use inverse Fourier transform to reconstruct the image, and there is no data loss. So it is the energy preserving property. If we convert a real image to its Fourier domain and back, then the results are still the same. Okay, so let's see an example. So given the box function hx, with a small range x, the value is 1. Otherwise, all of the value is 0. So what is the Fourier transform of this function? Make a guess. Of course, you know the answer is on the next slide. All right. Let's go through those equations. So by definition, this is the Fourier transform. The hx is here, and it times the exponential term and the integral. And because this is a box function, so all of the values out of the range are 0. So the integral is the same as the negative 2 half of x to positive half of x. We don't need to care about the remaining range. So as you know, to integral exponential function, the result is still an exponential function. So this is the exponential function, and it is different from the beginning end term and the beginning value. So we will move the coefficients to the this part and put in the half of x here and the positive half of x as the x here. So be careful of the small x, it is a variable, and the capital X is a given value. Okay. Then we expand the exponential function as a sine and a cosine function with an imaginary unit z. So this is the first term from here, and this is second term from here. And you see, because cosine is a symmetric function, it means for positive theta and negative theta, the value is the same. So the two terms are removed because they are the same. And then we get this function, equation. And they are the same. So we combine that together. And we slightly adjust the coefficient. Move the two negative signs are removed. So the two, move the two here. And the J and the J, they are removed together. So this is almost the result. And we slightly move the 2 to the denominator and add x here. Okay, so this is the final result. And this is the sinc function. This is the definition of the sinc function. Okay, so you can see from given a box function, and its Fourier transform will be a sinc function. And there are some pairs. Okay, so for box function, we get a sinc function. For a Gaussian function, we will get another Gaussian function. And from a sinc function, we will get a box function. Okay, so for previous slide, you see the mathematical definition of a Fourier transform for continuous function. And there is also a discrete function. Okay, it is the meaning are almost the same, but for discrete image data such as image, we are not able to use the continuous format of the Fourier transform. So this is the discrete definition. Okay, the same given an H. Okay, we have only the sample point at a certain value, x. Then from x to 0 to n minus 1. So you see, this is the exponential term. It's almost the same. Okay. Then we will get this is the result of the Fourier transform for discrete domain. Also, there is the inverse Fourier transform. The format of the transform is almost the same as the continuous version. Okay, so this table is copied from your textbook, okay, and section 3.1. And this is some widely used image filter. So box, linear, bilinear, Fourier. So you have seen Fourier in our previous course. Okay? And this is its kernel. And this is its transformed result. So if the author of our textbook draw their curves for each filter, okay? So now let's do some exercise from the kernel to the transformed result. So for the Fourier, you are quite familiar with this filter. The definition of the discrete Fourier transform is something like this. But take a look of this is a formal definition. But this is the equation used by our textbook author for this table. Okay, so you can see the equation here. The authors use this. It's very similar to the official definition of a discrete Fourier transform, but not totally the same. Okay, then, okay, if we follow the author's equation, the result will be, so h, when k is -1, the result is half, negative half. And when k is 0, the value is 0. And when k is 1, the hk is half, right? So we combine the three terms together. Because this is 0, so we remove this term. And we got the summation of this. When we expand the exponential into sine and the cosine, because this is negative, so this is cosine omega minus j sine omega. And then we remove the cosine term because this is negative, but this is positive. So we combine the two terms and get the final result. So take a look. This, right? The function is the same. The only difference is the coefficient. Let's do another exercise. So this is the box 3 filter, and this is definition of a Fourier transform. For k as -1, the coefficient is 1/3, and for k as 0, coefficient is also 1/3. For k is 1, coefficient is the same. So we combine. Okay, so for k as -1, 0, and 1, we put their values into the equation. So this is negative, so we got a positive exponential term. And because this is 0, so exponential to 0 to the order of 0 is 1. So we get the 1 here, and this is 1. So this is exponential to minus j omega. That expands the exponential term, cosine and the sine. Cosine and the negative sine. Okay. Then we remove the cosine term for both value and combine them together. So this is the constant term, 1/3. And the first cosine and the second cosine, we combine their coefficients to get 2/3. So this is the final result. And let's take a look of your textbook's table. totally the same. Yes. Yes, please. Hmm?
When you go back to the calculation, that one third one plus cosine omega, but it should be one third one plus two cosine.
Oh, really? Okay. Where? Which one?
The last.
Right. Sorry, sir. There should be two. Thank you very much. I missed the two here. Right. And let's take a look of the. Right. The textbook is right. So, thank you very much. And so this is why I call this is tentative slide, because I believe I have a lot of errors in my slides. Okay. So let's think about its computational load. So for Fourier transform, this is the definition of the discrete Fourier transform. What is the order of complexity to finish the transformation? Let's do a calculation. Okay. Given, so K will be from negative f of n to positive f of n. So there are totally n values of the transformed function. Okay. Then given a K1 value, if we want to calculate it, the complexity is order of n y. Because see, this is x from 0 to negative 1. So there's totally n values. So we need to calculate the n times of hx and n times of exponential and then sum them up. So the complexity of a given k value is order of n. And how many of k values are there? Totally n, right? So to calculate the one k value, we need n times order of n calculation. So the overall is n times n. So this complexity is n squared, quite large. Okay, and some researchers, they have developed algorithms to generate the Fourier transform results quickly, and that is fast Fourier transform algorithm. And this is idea, just idea. We are not going to prove it. Okay, the idea is the n is to certain order. Okay, then we can divide them into different parts and then calculate the value and merge them together. So, for example, say n is 8, so it's 2 to the order of 3. Okay, so x is the input function. Then we can calculate x0, x4, x2, and x6, and then combine them to some intermediate value. And then those intermediate values will further combine with a certain value. And finally, within 1, 2, 3, 4 steps, we can generate the value of the Fourier transform. So it reduces the complexity from order of n squared to order of n times log n. So this is only approach. It's called decimation in time. Another, so see, take a look at this. So the result of the Fourier transform is 1, 2, 3, 4, 5. It's a sequence at the end. But the input is not in the order. Okay? Another way, there's another similar algorithm. It goes in decimation in frequency. The input of the function, the order will be 1, 2, 3, 4, 5, 7. With those calculations, the output result will be 1, 4, 261. So either way, decimation in frequency or decimation in time can generate the result, and all the stuff. The complexity is the same. The only difference is how they execute those calculations. So we discussed about the one-dimensional or single variable univariate function as Fourier transformation. Now, if we have two variables, because all of our images are 2D data, so there is a two-dimensional Fourier transform. So that's the definition. Given an fx, then we find is exponential of the term ux plus vy. Okay, and it's also the integral from negative infinity for x and the integral from negative infinity to positive infinity to y. Okay, so u and v are the spatial frequency for the x and for the y-axis. In general, the result fx is complex number, and there are two parts: the real part and the imaginary part. And we use the notation absolute of the f Fourier function as the magnitude spectrum. And the division of the imaginary part and the real part is the phase of the angle spectrum. Okay. Like the univariate Fourier transform, there is also an inverse Fourier transform. So similar, the only difference is the term. So this is negative and this is positive. It converts images from the frequency domain back to the intensity domain. Okay, now some important Fourier transform pairs. So you have seen the univariate box. Sorry, univariate box function, right? Let's take a look back. Okay. This is the one-dimensional box function, and its results are a sinc function. Okay. Now let's go back to the 2D data. For this, for the vertical axis or horizontal axis, either is a box function, okay? And its result is a sinc function, but for two dimensionals. So this is the visual display of the sinc function for 2D, and this is the mathematical equations. Okay. See, we have processed the sinc function for 1D in this slide. Right? Remember, we did it before. Okay. From the box function, we get a sinc function. And now let's take a look of the 2D case. Okay. Use the definition. Okay, because the exponential times another exponential will be the summation of the component term here. So the exponential value can be separated to two individual exponential values here. So it becomes two individual box functions. Okay. So we got the final result is the multiplication of two sinc functions, very similar to the one-dimensional version. Another is Gaussian. Okay, so this is the Gaussian two-dimensional Gaussian function, and its Fourier transform is also another Gaussian function. Okay, how to prove it? I should say for box function, it is easy to calculate to prove it. But for Gaussian function, how to prove it? Okay, I found a version from the internet. It's very interesting, but there are many equations. Okay, so let's take a look. Okay. We want to prove, so this is our theory. The Fourier transform of an exponential function is still an exponential function. The only difference is the coefficient. Okay. So to prove it, we need two lemma. The first one is the integral of an exponential function from negative infinity to positive infinity for this term. The result is the square root of pi. Right? All right. So how to prove it? So this is the integral term. Then its square will be its times itself. But we use different variables. One is x and another is y. Then we can combine x and y because both of them are exponential functions. Then we set x as r times cosine theta, y as r times sine theta. Then dx dy will be the radial result. And then we can convert this term to this term. The only difference, dx dy becomes r d theta. Okay, this term becomes minus r squared, and integral this part. So this is from 0 to 2 pi. Then we get the result, and from 0 to infinity. So as r as 0 to infinity, it means 1 and 0. See here, when you put r as 0, so e to the 0 is 1, and e to the negative infinity is 0. So we get the result as pi. Therefore, the I value of this is the square root of pi. And we need another lemma. It means for a given value b greater than 0, then the integral of the exponential term, it will become square root of pi together. So, okay, this is the proof. Okay, this we need to use circular integral. And okay, from here, it can be separated as 4 parts. So this is negative a to a. It means from negative a to a, and from negative b to a, from this to here, and a to negative a. So this part is this to this, and this is 0 to negative b. It is the imaginary part. So this is 1. So this is a circular integral. Because of a circular integral from it's the same point as the beginning and end. So the result is 0. Then okay. Because this is 0, so we move 2 parts to the left side and 2 parts in the right side. Okay. And because this part is less than this part, and when the a goes to the infinity, the value becomes 0. See here, because e to the order of negative infinity is 0, so the overall term is 0. Therefore, we got the same term will become the same. So, because this term we have seen it before, this is a lemma 0.2. So this is negative pi. square root of pi. And finally, we can prove the theory. Okay, so this is the definition of convolutional Fourier transformation. And then we put those terms together because this is the multiplication of two exponential terms. Then we move some terms out of it, and the integral is, and the remaining part will become the square root of pi. So this is the final result. Okay. So this is what the author wants to prove. The exponential, the Fourier transform of an exponential term is still an exponential term. Okay. So let's go back here. As we mentioned before, Gaussian distribution, so Gaussian filter or Gaussian distribution, it is a separable filter. It can be separated into the x and the y axis. So here, once we prove the Fourier transform of an exponential term is still an exponential term, then let's go back here. For the axis, it is transform result is the exponential term. For the y-axis, it is still the exponential term. So the result is also finally a Gaussian distribution. All right, so let's go to the third pair. So this is a circular disk function. Okay, we see in the circular, the value is 1. For other regions, the value is 0. Then the Fourier transform result will be a Bessel function like this. Okay. And this is another example. It's called a direct delta function. Okay. So the direct delta function can be viewed as a limitation of normal function or Gaussian function. Okay, it is when the variable is 0, then the function value is very high. But for all other values, the function value is 0, but the integral of this function is 1. So let's take a look. Okay, so for different a, when a becomes smaller and smaller, you can see the function become higher and higher, and become very, very, very narrow, like an impulse. This is the definition of the direct delta function. If we transfer the direct delta function to Fourier domain, so what will be the result? Okay. So this is a direct delta function, and its Fourier transform, if we integral the function here, because the function has value only at the location of 0, 0. For all other regions, the value are all 0. So the integral result will be this is 0, 0. This will be 1. The result will be 1. So it will become a plant. All values are the same. And if we have two direct delta functions, then what will be result? So this is one of them, another of them. The Fourier transform will be the combination of the two functions, and so it will become a cosine function. So for a cosine function, so what it will be? You will see a lot of horizontal patterns. Let's see another example. Okay, so for this, okay, this is the given image. So you see a lot of slightly sloped patterns in the input image. So what will be their Fourier transformed result? It will become two direct data function. And when you increase the frequency, then what will happen? You will see the location of the two direct Fourier function will be farther apart from the origin. And also the direction, you see, from the original part to the direct point will be the same as the direction, the normal part of those lines. Okay, if you further, increase them, then you will see the input image and the result. Okay. The frequency was increased. Okay. So for signal, because signals can be composed, so for this one, this is the image, and this is the Fourier transformed result. This signal plus this signal, it will become the combination in the frequency domain, like this. So now you have certain knowledge of the frequency domain, and you have the tool. Then what can you do? Okay, let's see some examples. So we can filter the frequency and the spatial domain. So this is the image filter you take a look in our previous course. Given an image and given a software filter, and if you use the software filter to fill out the input image, so you can get, this is the vertical edges, right? Okay. How to do it in our frequency domain? It will be like this one. Given an input image, we convert the image into the frequency domain using fast Fourier transform. And given the filter image filter, we also convert it to the frequency domain. Then remember, the convolution in the spatial domain will be the product of their individual Fourier transformation result. So this, we multiply this image by this image point by point. This is the generated result. So here, the red color means a large value, and the blue color means a very, very small value. Okay, so if we multiply this image by this image piece by piece or point by point, it means for those regions, the Fourier transform result multiplied something very small, like 0. So the results are still 0. And for the central regions, because their values are large, relatively large, so if we multiply a point here to its corresponding point here, so the result value is still large, right? And we get the multiply the image. We use inverse fast Fourier transform and get its filtered result. So one of the application of Fourier transform is to apply image filters. Okay, this is a long, I should say, MATLAB code. The same. I show it there because if you want, you can do it by yourself. Okay. And let's explain it piece by piece. Okay, first, I load an image. So this image called Barbara.jpg. Then I convert the image from color space into grayscale because fast Fourier transform it only works for grayscale image. Color image means an image has 3 different channels: green, blue, and red. Okay, and the RGB to gray functions. Do you remember there is a matrix when we discussed colors in our previous slide? If we convert RGB space into another space like a YCBCR, let me show the slide again. Here, so this is the equation from RGB space to YCBCR. So this is the coefficient for RGB. Most of them are green because green is most likely to the intensity of brightness, and blue is the most weak one. Okay, and they will like this. So this is Y, the brightness. Okay, so from the code here, it's doing the same thing. You can think the function RGB to image is like RGB to YCBCR, but get rid of the YCBCR channel. Only keep the Y channel alone. And then I need to convert because for the JPEG image, the unit is on-site integer from 0 to 255. But if we want to execute the Fourier transform, we need a floating point. So I convert the on-site integer to floating point, get the image, and I show the image. So this is the input image. Then I get the resolution. It is the image height and image width. MATLAB has the built-in function FFT2. It means fast Fourier transform for 2-dimensional. Right? Then, all right, time to break. And let's keep going on. So here we use the fast Fourier transform function for 2-dimensional image. And okay, the result is INFFT. And I use the absolute function because the result of a fast Fourier transform is complex. So if I want to show the image, then I cannot show the imaginary part, right? So I use absolute function to convert the complex value into a real value. Okay? And then I use image SC to draw the image, and this is the result. So do you see anything on this image? Very difficult, right? No, yeah, that's right, very difficult. So where is my result of a fast Fourier transform? Okay, the problem is the scale. Most of the values are very small, around 0, close to 0. And there is, or there are, some values is very large. How large? As large as 10 to the order of 4. So it's quite large. And where are they? So if I convert it to another image, so the only difference between the previous image and this image is I use a log function here. It's a log. Why? Because the scale is too large. It is difficult to observe. But if I use the log function, then the scale reduced to -5 to around 12. So it's easier for us to observe. So you can see there are some values. and the extremely large values are at the four corners. That's the reason why we cannot see them here, because they are at the four corners. Okay. So let's see. So what's the meaning of here? So imagine, let's recall this. We have a property. Fourier transformation of a real signal is symmetric about its origin. And where is the origin? Okay, you see, this is the origin, right? Suppose this is the origin. So the results are almost symmetric, but the sentence there in that slide is not meant this origin, but this origin. So from this, you can see the pattern in the image are very symmetric. So this is the yellow line here. So this is also yellow line here, and this is some yellow pattern here. This is symmetric. So let's go back to the sentence. This sentence, Fourier transform of the real signal is symmetric about the origin. It means this figure. So what's the difference between this figure and this figure? There's only a half image offset vertically and a half image offset horizontally. How to do it? So MATLAB provides a function called FFT shift, fast Fourier transformation shift, for users to easily observe the symmetry of the generated image. And let's go back here. Okay. So what's the meaning of those regions? Okay. So this is the result. Imagine this is the metric of the fast Fourier transform. We see a lot of equations, right? So this is the real result of those equations. And this is a slight offset image for us to easily observation. Okay. So if we want to explain the meaning, we need to start from here. Okay. So that's it. This is the metric generated by the equation of fast Fourier transform. So this region needs the high frequency signals of the input image. Okay, so what is the high frequency signals of this image? So this texture, this wave, and there are textures of the tablecloth, and there are some textures of the scarf, and about her pants. So those are the high frequency signals. They are, after Fourier transformation, they are in fact in this region. And at the four corners, there are low frequency signals. So where are the low frequency signals? For example, the floor, or the wall, those are low frequency signals. Okay? But for easy observation, many people like to shift the low resolution region to the center and put the high frequency signals at the four corners, right? So let's take a look. Okay, now I create a Gaussian filter. So I use f special, the function, and assign the name of the kernel as Gaussian, and its size is 2 times of 20. 20 means half of the filter size. And the sigma, or the radius of the Gaussian distribution for 2 dimensional is 2. So this is my result. Here, okay, I need to slightly change the location of the filter. So this is the filter I created. So how large is the filter? You see, because half of the size is 20. So 20 times 2 plus 1. So it is a 41 by 41 matrix. Right? Okay. But how large is my input image? The input image is 512 times 512. So the filter is smaller than the image. Okay. And for MATLAB, there will be a problem. If I don't use the circle shift to move my filter to the center, then my generated result will be offset. So here, I move my filter to the center, but however, the center of the image, in fact, are the four corners of this image. Okay, so here, okay, this is the result. I move the filter, use circle shift, and the half of the filter size. So the actual result is I move my shift to the four corners. Then I check it. Okay. So you can see if I use FFT shift, FFT shift means the signal at the corner will become at the center, right? So after using the FFT shift, I get an image. That means my filter is at the center. So it's right. That's what I want. Okay, and the size of the filter becomes as large as the input image, 512 by 512. Then I apply the fast Fourier transformation to my correct filter. So this is the result. Okay, and I draw it. So you see, again, this is imagine this is the matrix generated by the fast Fourier transform. So the meaning of at the four corner means the low resolution signal, and the location close to the center are the high resolution, high frequency signals. So when I transform a Gaussian filter to the high frequency sonnet, so what does it mean? It means for low frequency signals, the magnitude is large. For high frequency signals, its magnitude is small. And then if I use FFT shift, then okay, this is the result of FFT shift. It means I will preserve most low frequency signals and reduce high frequency signals. Okay. Then I do multiplication. So this is a pixel by pixel or element by element multiplication. This is the image of my Fourier transform result of the filter. And this is the image of the result of the input field image through fast Fourier transform. I multiply the two matrices element by element, get this result, and I show it this. So here you can see I preserve most low frequency signals and reduce the most high frequency signals. Finally, I use inverse fast Fourier transform to get a real image. So this is the result. It looks like blurry. So because most high frequency signals are reduced by the Gaussian filter. And let's recall the Sobel filter. Okay? We saw this filter in our previous course, and this is the input input image with the filter, we can find the horizontal edges, right? Okay. Then in MATLAB, what will we do? Okay, so this is the MATLAB code. Okay, and it's very similar as the previous code, the Barbara one. So what I want to show you is the result of the Sobel filter. Okay, so for this Sobel filter to detect the horizontal edges, this is its fast Fourier transform result. Oops, again, this is the original one, not shifted, and this is the shifted one. So for this region, what does it mean? The color here is very red. It means large magnitude. So the filter preserves most horizontal signals because the image is symmetric about the origin. So I just use one single rectangle to show it. Okay, and the result. So let's see another Sobel filter. So, but this time it is used to detect the vertical edge, and we will get the fast Fourier transform result. Again, I highlight this region because the filter preserves most vertical signals. How about the derivative filter? Derivative means a pixel minus its right pixel. So this is the derivative filter. Okay. So the result would be, okay, so this is the result. Okay. And because the input image, the range of it is 0 to 255. So 1 pixel minus the intensity of its right pixel, the range will become the maximum possible is 255. It's 255 minus 0. And the minimum number, possible number, will be negative 255. If this pixel is stuck 0, but its right pixel intensity is 255. So 1 minus another, the result will be negative 255. So see the range for the image. It is from 255 to negative 255 to positive 255. Okay. So that. So this is not an image for intensity. The color or the brightness here is used to express the real range. So most of them you see it's close to 0. It's the middle gray. And for the bright part, this like the white part, the derivative value is high, around 255. And for the dark side, for this dark line, because this pixel at along the edge is very low, say 10 or 20, but the right pixel is very bright, say 255. So you can see the dark pixels along this edge, and its value is around negative 200. Right? When we use fast Fourier transform to convert this filter to its frequency domain, this is the result. Okay. And you can see, so there's very small values along to the vertical line. The meaning is it will reduce the vertical signals no matter what the frequency is. Okay. So let's go back here. When we apply this directive filter, our result, what do we still remain? We only have some vertical signals here. And the horizontal signal, for example, along the shoulder, we cannot find it in our result because it is a vertical signal and it has been removed through this region. All right, so there are a few questions. So which has more information? Because you know the Fourier transform will create the value in the complex domain. And in the complex domain, there are two components, the magnitude and the phase. Which is more important? Okay. And what will happen if you take the phase from one image and combine the magnitude with another image? So that is a hybrid image. Just keep it in mind. You don't need to answer it right now. And let's see more examples. So remember, there's a problem of the projector. Well, again, it's difficult for you to see the AG artifact in the right image if the image is filtered by a box domain. But if you have a laptop and see this slide on your laptop, it is easier to spot those artifacts. So it means when we apply a Gaussian filter, there are no AG artifacts. But when we apply a box filter, there are many AG artifacts. And the reason, let's recall this. Okay. When we apply a Gaussian filter in its frequency domain, the pattern looks like this. So this is the input image, and this is frequency domain signals. This is a Gaussian filter, and this is frequency domain signals. We mean when we convolution of the spatial domain will equivalent to the multiplication on the frequency domain. So this is the result of the multiplication, and this is the result of its convolution in the spatial domain. And when we use it box filter, the signal domain of the frequency domain of the input image are the same, but the image in the frequency domain of the box filter, remember, it is a two-dimensional sinc function, right? So it looks like this. When we multiply the two images, we will get this result. So compared with this image and this image, you can see there are several high-frequency signals along the horizontal and the vertical axis. So that is the reason of the AG artifacts if we apply the box filter. Right? Okay, now let's do a small exercise. There are 5 images in the frequency domain, and there are also 5 images in the intensity domain. So now, which one is which? One image to one frequency domain. Oh, good. Keep it in mind. Some of them are easier, some are slightly difficult. All right, are you ready? We will show the answer. All right, this is the answer. Okay, for this, it's easy, right? Because this is the Sobel filter. And of course, this is so we have seen this already. And this is Gaussian. So this is Gaussian too, right? Okay, easy. And for this, you can see there are many horizontal waves, right? Okay. Because this is a sea, okay, there are many waves here. Then their direction are horizontal. So it generated this high-frequency domain. Along this vertical axis, the signals are slightly larger compared with the two images. Okay? And for this, you can see there are some large vertical and horizontal signals. They are the edges in the image. Okay? So we generate this result. There are some large vertical and horizontal signals. And for this, there are no apparent horizontal and vertical signals, because for these images, the signals for every direction are almost the same. So we get this image. Okay. Now, let's go back to the questions we asked. So when we generate a low resolution image, what do we lose? We lose the high frequency signal, right? Okay. And if so, then given an image, what is the good way to generate the low resolution version? When we subsample or when we generate the low resolution, we will lose the high frequency signal. So how we preserve certain high frequency signals from the high resolution image to its low resolution version. Okay, so there's a straightforward approach is just subsample. We don't need to care about anything because an image first is a two-dimensional data, right? If we want to reduce the image size by half of it, then what do? Use a value, skip another one. Use another value, skip another one. So we will generate this low resolution image. But let's see some facts. Okay, so given this image, right? Okay, if we just subsample one pixel and skip another, then what will be the result? This. Okay, we do it once and do it another one. So you see there are many pixels. Their neighbors differ a lot. So this is called aliasing. If we just directly subsample some pixels from the original image. So let's take another example. Okay, given a chessboard, and if we subsample those points, then we will get this result. It looks okay. If we slightly reduce the number of subsampling points, it still looks okay. But okay, if we subsample then at a wrong frequency, so this is the result. Okay, so this is the original image. Okay, for 4 pixels, or no, I should say so. If we subsample it here, then we get the black result. But we subsample it here, we get a white pixel, and then it is white. So this is the generated low resolution image, and then this is the original high resolution image. Some of us will feel, no, this is not what I want. The result doesn't look like the original version. Okay. And if we change the subsample frequency, so for this chessboard, we subsample the first point here and the second point here, we will get black and black. The same, this will be black, black. So we will get an image, all of the pixels are black. So for some of us, that is not the result they want. So let's see another example. Okay, this is the image. Looks like some very old video game or something. So there should be a line here from this pixel to this pixel, right? imagine. So this is another line from this to this. But however, when you see some points far away from it, the line disappears, and you see there's a region of white pixels. So this is also the problem of aliasing. Okay? Let's see another. So this is for image. And for video, there is also the aliasing phenomenon. So let's take a look. So this is the pole. Go. Okay, sorry, why can how to control? All right, so okay. So do you see the pattern? So this is this looks like a chessboard, and they are black and white pattern. So when we rotate the board, ideally we should see the circles in the same direction, right? But because of the sampling problem, some of them are moved under another direction. So that is the aliasing problem in video. Okay? So this example, this is the Fourier, and the Fourier is rotation. When we sample the frame here, okay, we see the point this, and ideally we will see the point here. So it looks like a slide. But if we change the frequency of subsample, then we may see the wheel is not moving, or it rotates in another direction. Okay. So there is a theory about the sampling. It's called Nyquist-Shannon sampling theory. So for every signal, because now we know Fourier transform, every signal can be expressed as the combination of some sine and cosine functions. Okay, the theory says, given a signal, we think it is a combination of many signals in different frequencies. Then there should be a maximum frequency. Okay? Then the sampling rate, if we want to reproduce another signal, it should be greater than 2 times of the maximum frequency. Okay? For this example, the curve is a signal, and the black points are the sampling time. Okay? So for this, you can see this is the cycle of curve of this curve. Then we use 1, 2, 3, 4, 5, 7 times of the sampling rate to sample this signal. So we can well reconstruct the input signal. But for this, if our sampling rate is too low, then we cannot reconstruct the signal well. So now we know if we sample signals directly, then there will be an artifact called aliasing. So how to solve the problem? The easiest problem is apply a Gaussian filter on it and then sample. So that is the anti-aliasing approach. Okay. So this is a MATLAB script. It means we create a Gaussian filter and apply it to the image. So we get a blurred image, right? You have the experience. Then we sample those blurred image. It is 1 to n, means start from 1 and skip the second pixel, and then get the third pixel, skip the fourth pixel, etc. from 1 to the end of this dimension. And this is our result. It will be, okay, this is the input image. Apply Gaussian filter and subsample. Apply Gaussian filter and subsample. So if we enlarge it, it will look like this. Compare with this. This is the result without using the Gaussian filter. And you see the aliasing result. And compare with this, there are less aliasing. But however, there is an issue. How do you know how large the kernel of the Gaussian filter should be? Okay? If you use a very large kernel, then everything will be very, very blurred. But if you use a very small Gaussian kernel, then there was almost no effect for the anti-aliasing image, right? So the parameter of the Gaussian kernel, you need to tune it, and nobody knows what is the optimal parameter. Okay. So let's go back here. Now you know when we generate the low resolution image, we lose the high frequency signal, and if we want to prevent or reduce the anti-aliasing problem, we can apply a low pass filter. In particular, Gaussian is the widely used one to remove combine those high frequency signals together and preserve it in the low resolution image. So there is a term called image pyramid, like this. Given an input image, we apply a Gaussian filter and subsample it to generate the low resolution version. And furthermore, apply a Gaussian filter again and subsample it again. So we get a further smaller image, as 1/4 of the original one in terms of the width or height. Okay. Then finally, so it looks like a pyramid. At the base, the resolution is largest, and with one level up, then the resolution reduced 1/4, and further. Let me show you an example. Okay. So this is the input image. The resolution is 512 by 512, and we apply Gaussian filter and generate the low resolution one. So its resolution becomes 556 square, and then 128 square, 64 square, 32 square, and 60. So this is the resized result. So you look like they look like they look like as large as the others. And then this is the original, I should say, actual size. So this is 512 square, and it become 1/4, and the further become 1/4. So if you put them in a layer by layer, it becomes a pyramid. This is a Gaussian pyramid, and then there's another pyramid called Laplacian pyramid. So what's the difference? The difference is here we apply Gaussian filter and then subsample that. But so this is the input image. We apply Gaussian filter and subsample that. So for this column, it is a Gaussian pyramid, the same as this one. But if we apply a difference between the input image and the image filtered by the Gaussian kernel, we will get the difference, right? Oh, so, and for the first layer, we get a difference. For the second layer, we also get a difference. For the third and the following layers, we all get a difference. But for the latest layer, we keep the intensity 1, the very small intensity 1. So this pyramid called Laplacian pyramid. Compared with Gaussian, all of them are intensity. But in Laplacian pyramid, only the smallest image is the intensity, and all remaining layers are differences. Okay. So this is the figure in your textbook. Okay. So given an input image, I should say there are several ways to create a Laplacian pyramid, and this is the one mentioned in our textbook. Given an input image, we apply Gaussian filter, low-pass filter here, and the symbol here means downsampling. Downsampling for 2 pixels, pick 1. So this is 2 to 1 downsampling operator. We get the low resolution intensity image. And we upsample the intensity 2, means for the low resolution image, we increase, I should say, we put the pixels here to a twice large image and copy the pixel value from a point to another point and keep zeros in the pixel in the middle. Okay. This is upsampling step. I means interpolation because there's no value for the pixel in the middle. Okay. So it applies the interpolation to create the high resolution image. Okay. So this is similar like this. Okay. And then the input image will minus the reconstruct the image pixel by pixel. So it will get the differences like this one. In this case, it's like this. And apply it for every layer. So it will generate a sequence of image like this one. So it is also a series of difference layer and finally an intensity layer. Okay. So this is another way to create a Laplacian pyramid. Okay. So what can it be used? So this is the example. It is called Laplacian pyramid blending. So this is an apple, and this is an orange. If we use the half part of the apple and the right part of the orange through a Laplacian image pyramid, we will get an image. The half part looks like an apple, and the right part looks like an orange. Okay. So this these are the image class by your textbook. Okay. So this is the high frequency, most high frequency for the first layer for the apple, and this is the second layer of in the Laplacian pyramid for the apple, and this is the low resolution intensity layer. Okay, this is for this column, it is the orange part, and if we combine them layer by layer, this is the first difference layer, second difference layer, and then intensity layer, and see here. We create a Laplacian image pyramid from an input image, right? So given a Laplacian image pyramid, we can reconstruct its input image. Okay. And this part is the reconstruction. Given the low resolution intensity image, we upsample it and interpolate it, and then we add its difference layer back. Then we get a